All right, we're going to pick up in our discussion of r squared where we left off in class today. So just to remind you what we were doing, we had a population relationship that looked like this, happened to be a bivariate equation, meaning 1x, 1y. We know that because it's a population example, we have to add a stochastic error for all of the reasons that Studeman talks about. From that, given a sample of data, we would estimate the parameters, b hat, beta 0 hat, beta 1 hat in this case. And when we apply the beta hats to our x, we would have a predicted y. So this is the equation of the estimated regression line. Okay, so it's an estimated regression line. It's not the whole scatter plot of points. If we wanted the scatter plot of points, this would become a y, and we would have to add a residual to that equation. Okay? So what we did in class was we argued that this thing called the total sum of squares, abbreviated TSS, is really what our regression model was setting out to explain in some sense. So we have this y variable of interest. It goes up and down. In other words, there's variation in it, and it's that variation that we would like to explain. The r squared statistic is going to be the fraction of the variation in y, that is the fraction of the TSS that's explained by our regression. And so the question is, how do we capture that explained notion? So we began the process of doing that by writing out the formal expression for total sum of squares, that which is to be explained. And through a little bit of algebra and a bit of hand waving, we ended up with two distinct components. This one is called the residual sum of squares, and this one in today's class was referred to as the explained sum of squares. Okay? So the question is, how is it that we can talk about this thing called the explained sum of squares? I think this is one of the most confusing, conceptually challenging ideas in the first few chapters of the text. So here's what I want you to think about. I want you to imagine that we have a scatter plot of data. Okay, there happens to be a specific point already noted in this, but let's suppose that we have a scatter plot of data. It might look something like that. And let's suppose that we didn't know the x values at all, and we didn't have, therefore, an estimated model. All we knew, in fact, was y bar, the mean of the y's. And I asked you to predict if we had to, what value for y might occur in some given circumstance. Okay, so we used the height weight example in class. If the next person who walks in the door is such that I can't see the height, but I know the average weights up to that point, what guess might I make, or estimate might I make about that person's weight? Well, I might use the mean as my guess, right? So here roughly is the mean of the y's, and absent any information about x, absent any particular model to work from, I might simply predict weight with the average that had occurred up to that point. And we could extend this to mean anything, right? I mean, we could try to predict wages in a particular occupation, or we could try to predict stock market prices in a particular week, or whatever, based on the means. So now let's relax that restriction, and let's suppose that we have some meaningful x variable to work with, that we in fact can go ahead and estimate our model. So we have beta 0 hat plus beta 1 hat x to work with now. And we want to come up with a statistic that's going to capture the extent to which our model and knowledge of x is going to improve upon, on average, our prediction of a given y value. So the idea here is that if we didn't have that x, and if we didn't have that estimated model, we might predict our y value with simply the mean, and the difference between y and y bar would be the extent to which we, quote, missed the mark. It would be the extent to which we predicted wrongly about that particular y value. Okay? Similarly, we could pick another data point. We could pick that one, and we might have predicted y bar, and that deviation would be the extent to which we missed our mark based on our average alone. All right? So now what we're trying to get a sense of is this ESS, which you'll recall was yi hat minus y bar squared. Oops, that's supposed to be a squared. There we go. But to get any sense about what that means, we have to understand this part, the y hat minus the y bar. So remember, what I've circled here is the extent to which we would have mispredicted had we had only the y bar average to work with. So then what is y hat minus y bar? Well, that's this distance. And you can see visually in this diagram that that is the extent to which we have come closer to predicting correctly that particular y, because we now know y hat and x. Okay? So this is called the explained sum of squares because it's a statistic that adds up for the whole sample a measure that represents the extent to which we got closer to the true y for having known x, our estimated coefficients, and therefore our predicted y. In that sense, this can be referred to as the so-called explained sum of squares. Now, the definition of R square is explained sum of squares divided by total sum of squares. In that sense, that's where our verbal explanation comes from. The fraction of the variation in y explained or accounted for by our regression. Okay? Now, because TSS from the last slide is ESS plus RSS, we can divide through by TSS to just rewrite this a little bit. And what we end up with is 1 equals R squared plus RSS over TSS. Okay, now why is that useful? Well, we can now rewrite R squared in a second way. So R squared is ESS over TSS, but it's also 1 minus RSS over TSS. And don't forget what those are. This RSS is the sum of the EI squared, and the TSS is the sum of the YI minus Y bar squared. Okay? So don't forget what those are. All right? So two ways of thinking about R squared: the fraction of the variation in Y that's explained by our X, or 1 minus the fraction of the variation in Y that is not explained by our X and our model. Okay, this next set of diagrams is related to what you will see in your spreadsheet exercise once I give it to you. This is an example of a case where R squared is 0, and in fact when you look at this particular scatter plot of points, it's very difficult to know what the line should look like. Should it be like that or like that, etc., etc. In that situation, the R square is going to be very, very low. The next one comes closer to one of the panels that we saw in class today. This is a case where the data points are clustered very tightly around the line, so the residuals are small, therefore the sum of the residuals squared is small, therefore the explained portion of the variation in Y is high, which gives us the R squared of 0.95. This is an extreme case, and you might think this is a great situation. It's actually not. Usually it means we measured something wrongly. Okay? If all of the data points in your sample sit on an actual line, then probably one of the variables is simply defining the other one. So here you've measured distance in feet, and maybe here you've measured distance in yards, or something. I guess that would not be the case because of the intercept, but you kind of get the idea. We've measured something so that one variable defines the other, and therefore there's really nothing interesting for an econometrician to look at. But when all the points are on the line, whether it's a positively sloped line or a negatively sloped line, the r squared is going to be equal to 1.